Yeah, so today we're going to be doing uniformity testing. Um, and just you know, to go over the problem and the statement, our aim is to property test if a distribution P is the uniform distribution, and we'd like to do it better than the sampling bound, which is just O of n over epsilon square. And indeed, there's a seminal result of Batu et al. That shows that the property of uniformity can be tested with square root n over epsilon to the fourth samples. And this was in 2000. In 2008, Paninsky gave the optimal bound of square root n over epsilon square. So, but Batu et al. Also observed that the dependence on n has to be root n. And this paper is actually a very seminal, important paper because it first posed this question of distribution testing formally. It should be noted that the root n over epsilon fourth bound was implicitly, or almost explicitly given in a previous paper of Goldreich and Rahn, although the Goldreich-Rahn paper was in a different context. But effectively what they had to do was to test uniformity for a distribution, and they gave this algorithm and the analysis. Now, the key to uniformity testing is going to be exploiting the birthday paradox. And let's go over a few basic facts. So for any p, the 2 norm squared is basically the summation over all elements of the support of the probability squared. And Cauchy-Schwarz says that this quantity is at least 1 over n. Now for the uniform distribution, it is exactly 1 over n. And it turns out this is going to be the key in the uniformity tester, is to essentially, if we can measure the norm, we will show that distributions which are far from uniform have a larger collision probability, have a larger 2 norm squared, and that will allow us to make this distinction. So the first step was to show this relatively simple equality, is that the 2 norm squared between the uniform distribution and a given distribution is basically the collision probability squared minus 1 over n. This is the 2 norm squared, which I also call the collision probability. So the 2 norm squared minus 1 over n. And doing a little bit of manipulations, we can show that if a distribution P is far from uniform, meaning that the distance to the uniform distribution is at least epsilon, then the 2 norm squared is at least 1 over n plus epsilon square over n. So note that if the distribution was uniform, then the 2 norm squared is 1 over n. If the distance is more than epsilon, then the 2 norm squared is more than 1 over n plus epsilon square over n. So this is the gap, right? So when your distribution is far from uniform, you know that the 2 norm squared is at least whatever it is for the uniform plus this additional epsilon square over n. Now, what is the 2 norm squared in terms of, as I said, we can interpret it combinatorially. This is the summation of I going, over all the support of pi squared. This is exactly the probability that 2 independent samples are identical, or that 2 independent ball tosses end up in the same bin. And this is exactly what we look at when we do a birthday paradox calculation. So the algorithmic idea is to estimate this 2 norm squared and then use the lemma to distinguish uniform from distributions that are far from uniform. And the idea, let me just so the idea is to the algorithm is going to choose some number of samples that I'll denote by S. It is going to count the number of pairwise collisions, that is 2 different samples with the same value, or 2 balls that end up in the same bin. And let's call this quantity K. K is the number of pairwise collisions. The algorithm is going to use K divided by S choose 2 as an estimate of the 2 norm squared. So the full algorithm, what it's going to do is, it's going to say if k divided by s choose 2 minus 1 over n is greater than essentially epsilon square over n, and we're going to put a 4 over there, a constant factor, just to just to take care of deviations, then it's going to reject. It's going to say, in this case, its estimate for the 2 norm squared is more than 1 over n plus epsilon square over n times some constant. And so it's going to reject. Otherwise, it's going to accept. This is the entire algorithm. And so the key is to figure out what is the choice of S that is required for this algorithm to work. Okay, any questions about this? Because we're going to launch into the analysis right now. Okay. So the key theorem that we need is the following. It says choose. Okay, so I'm going to set delta to be another parameter. You can think of delta is actually going to be set to epsilon square. But I'm going to keep the choice of delta just so that you have this theorem as a sort of standalone theorem. So let this random variable, which is the number of pairwise collisions divided by s choose 2, because you have s choose 2 pairs of samples. And what we have is essentially some kind of a deviation bound. So my apologies for that. We said the probability that x deviates from its expectation. So we'll actually show that its expectation is the 2 norm squared, the collision which is the collision probability. The probability that it's outside this range of 1 plus minus epsilon is at most 1/3. And you'll see that this proof is non-trivial, and this is because it is not easy to express. We cannot express x as a sum of independent random variables and apply a standard concentration bound. We have to be a little more careful and essentially go from first principles. So let's start with the basics. The expectation of x. So let's look at what is the expectation of the number of pairwise collisions. So I'm going to just use linearity of expectation to bound this. So this is the expectation. Now I'm going to sum over all a and b going from 1 to s. A and b are going to refer to indices of the samples. They're indices of the samples. So I'm also going to refer to balls and samples sort of interchangeably, because sometimes I want to really think of this. I had this visual view of the balls and bins. So A and B are referring to the indices of the balls or the samples. These are independently drawn. Now the expectation of the sum over A less than B of the Ath and Bth sample colliding. What is the probability that the Ath ball and the Bth ball end up in the same bin? By linearity of expectation. Now this is really important. The fact is these events, the Ath and Bth sample colliding, are correlated events. On the other hand, I can just use linearity of expectation. And so when I commute the expectation and the sum, I switch the order, I get the sum over A less than B of the expectation of the Ath and Bth sample colliding, the expectation which is technically of this event. I mean, this is somewhat poorly phrased. I should say an indicator for the Ath and Bth sample colliding. So this is the indicator for that. And so the expectation of the indicator is just the 2 norm squared, as we've discussed, and therefore the expected number of pairwise collisions is s choose 2 times the 2 norm squared, and the expectation of x is precisely what we want. Okay, any questions about the expectation analysis? Right? If not, then we can move on to bounding the variance of x. Okay, we can go on to bounding the variance of x. So I'm going to abuse notation a little bit over here. Let me just use x to be the number of pairwise collisions. And previously I was using x to be the number of pairwise collisions divided by s choose 2. Essentially, I'm just rescaling things. It's going to be more convenient for us. So x is the number of pairwise collisions, and we just argue that the expectation of x is s choose 2 times the 2 norm squared. Okay, now let's look at what the variance of x is. So I'm going to write x as a sum, exactly as before, of a less than b going from 1 to s of x a comma b. Now x a comma b is the indicator for the ath and bth samples colliding. Right? That's what xab is. So the xab's are not independent, and this is going to be sort of the major problem in our analysis. Now, before we actually launch into bounding the variance, let's try to understand what is it that we're actually looking for. So let's go ahead, let's apply Chebyshev and see what is the bound that we need on the variance for things to work. So Chebyshev is going to say the probability that x minus the expectation of x. What is the probability that this is, I'll say greater than delta times the expectation. So I'm just writing out Chebyshev here. So this is at most the variance of x divided by delta square times the expectation squared. So I'm just writing out what Chebyshev is. And so what we want is that the variance of x needs to be much smaller, small enough than this denominator. Otherwise, we're not going to get anything. So as long as we could get the variance to be at most, let's say in this case we get delta square expectation of x square divided by 3, then the probability of the deviation is going to be less than 1/3 as desired. So this is what we want to prove. Now the reason I'm writing it this way is, instead of telling you what the choice of s is and working with that choice, I instead want to keep s as a variable, sort of keep it as an unknown, and then tell you what is the math that shows the choice of s. So let us now move on to the variance calculation. Okay, so we have the variance of the summation of a comma b of xab. And I'm not going to sort of write out this in full detail. This is again all pairs. So it's a less than b, and a and b go from 1 to s, which is the total number of samples. So let us write this out. This is the expectation of the summation of xab squared minus the expectation of the summation of xab, where the expectation is squared. Okay. Now I'm going to use linearity of expectation to break all these terms apart. So let's walk through these a little carefully. So first I have, sort of the diagonal terms. So I have the summation of a less than b of xab squared. Then I have a summation of a less than b, a prime less than b prime, a prime, b prime, all distinct. Right, so each term, when I expand this out, is going to be of the form xab times xa prime b prime. I'm looking at the case where all these indices are distinct. So xab, xa prime b prime plus a third term where a is not equal to b or b prime, xab xa prime b, plus a fourth term which is b is not equal to a prime of xab x a prime b. So this is just expanding out the expectation of the square minus what I get from linearity of expectation over here is I can write this as the summation of a less than b of the expectation of xab squared. So note that this expansion is going to generate terms that look a lot like this, except instead of xab we actually get the expectation of xab. Okay, so does this make sense? All right, so let's sort of plow through these a little bit more. So let's look at the first expression here. xab is an indicator, so xab squared is equal to xab. So what I get over here is just the summation of a less than b of the expectation of xab. Right? I get the second term, summation of a prime, b prime, all distinct, of the expectation of xab xa prime b prime, summation a not equal to b prime, expectation of xab xa prime b, plus the summation of b not equal to a prime, the expectation of xab xa prime b, minus, okay, now I'm subtracting this expression out. Over here I get again summation a less than b of the expectation of xab squared minus the summation, and now I can just write this out as a prime b prime all distinct of the expectation of xab expectation of x a prime b prime minus some more terms, minus terms analogous to these, although I'm going to ignore them. Okay, what is this expression? What is this expression? Any comments?
That should just be the 2 norm squared, right?
That's or s choose 2 times the 2 norm squared. That is exactly the expectation. So this term is simply the expectation of x. Okay. Now let's look at this term. What can you say about this term? What can you say about xab and xa prime b prime when all of a prime b and b prime are distinct? What can you say about what can you say about these two random variables? Are they dependent? Are they independent? They're independent. Why are they independent?
Because whether like a prime and b prime coinciding
Exactly. We're talking about four independent draws or four independent samples from the distribution, four independent balls. So the behavior of what happens with A and B is independent of what happens to A prime, B prime, conditioned on whether A and B end up in the same bin. The event of A prime and B prime ending up in the same bin, has exactly the same distribution, and these are independent. So by independence, we can write this out as the expectation of XAB, expectation of XA prime B prime. Okay, does that make sense? By expectation, I can break the expectation of the product as the product of the expectations. And then observe that this term here is the same as this term there. Okay, I'll say this again, right? So XAB and XA prime B prime are independent, and by the independence we can break the expectation of the product as the product of the expectations. And so the second term here is identical to this term here, which is subtracted out, and therefore this cancels out with this. Okay, is this clear? So if you have any questions, please ask me. Questions? Okay. Now, are these independent? Is XAB and XA prime B independent? It's not obvious, right? And actually, potentially they are dependent because both XAB and XA prime B depend on the bth sample. Or XAB and XA prime B, yeah, that's right, both depend on the bth sample. I think I've fudged my indices here. This should actually be A prime, B not equal to A prime, and this should be, I've written the same thing here. I should write that, and then this would be A not equal to B prime. Sorry, mistaken indices. Okay, but does this make sense that one cannot break this product of the expectation of the product is a product of expectations? And this is really where the trickiness in the analysis comes in. Of course, if one could break it, then all of these terms would disappear, and what you would have here is essentially like a sum of independent Bernoullis or independent Poisson trials. So I could just upper bound this by the expectation of X plus the summation of B not equal to AA prime of the expectation of XAB, expectation of XA prime B, plus the sum of A not equal to B prime of the expectation of XAB, XAB prime. Okay, I'm actually going to sort of ignore all of these terms over here. This is what I get. And so this becomes the interesting term. So let's look at this sum now. Or let's actually look at the expectation of XAB and XA prime B, where B is not equal to AA prime. When is XAB XA prime B equal to 1? It means something here that we can interpret. When is this equal to 1? When all three of them coincide. So the A prime and the bth samples are identical. This is a three-way collision.
In this case, can A prime equal
A prime, no, A prime will not be equal to, I should also, yeah, you're right that A prime is also not equal to A, because if A prime was equal to A, that would be handled by this term here.
Oh, sure.
Sorry, someone has to mute. Hang on, mute. Right. Sorry, let me just mute everyone here. All right. So sorry, I've muted everyone, so you need to unmute if you need to speak. So I should write that over here in this term A is not equal to A prime and B is not equal to B prime. So everything, they're all distinct. A prime and B are distinct. So that means that you have a three-way collision. Okay, so now what is the probability that XAB XA prime B is equal to 1? What is the probability? I'm sorry, what is the probability that this is equal to 1? It's a clean expression. It's not messy. So what is that expression? Very similar to the two-way collision. You get the sum of pi cubed. Or writing it in norms, this is the cube of the 3 norm. Note that in this bound of the cube of the 3 norm also holds for XAB and XAB prime. Okay, is that clear? All right. So now, just putting it all together, the variance of X is at most the expectation of X plus, so we know the expectation of each individual term in the each individual term in the sum, and that is just the 3 norm cubed. How many terms are there? How many terms are there? S choose 3, right? Because you're looking at 3 different samples. And you'll get twice that. S choose 3 over here and S choose 3 over there. So this is going to be 2 times S choose 3 times the 3 norm cubed. Okay? And just to clean up the coordinate, some of the terms over here, let me just write this out as, so this was at most S squared 2 norm squared, and this is going to be at most S cubed times the 3 norm cubed. Okay, so let's go back to what we wanted. We wanted the variance to be at most delta square times the expectation square divided by 3, which is equal to, or this is let me just write this out. So this was delta square by 3 S choose 2 2 norm squared, and the whole thing was squared. Right, so we needed this to be delta square divided by 3. Essentially, this is something like s to the 4th power. So I'm just going to put an approximation here because I don't want to deal with the exact coordinates, but then we'll see what the choice of x will be and how things will follow. Ignoring the constants, the 2 norm to the 4th power. So what we want is for the variance, which is decided by s cubed and the 3 norm cubed, to be less than essentially s to the 4th and the 2 norm to the 4th power. And so a lot of distribution testing is about understanding the relationships about various norms of distributions and manipulating them. And so the key is we'll just use that the L3 norm is at most the L2 norm. And then what we get is that the variance of x is going to be at most the expectation of x plus s cubed times the 2 norm cubed. 2 norm cubed. Okay, now we can do a little bit of back of the envelope calculations to see what the choice of s needs to be. We want s cube and the 2 norm cube, that's this expression here, to be essentially less than s to the 4th times delta square. If you move things around, the s to the cube cancels out with that. This cancels out with that. And what you get is that s essentially needs to be 1 over delta square times the 2 norm. And so if we set s to be greater than, and I'm just going to put some convenient constant here. Let's say something like 10 divided by delta square times the 2 norm, then the variance of x is going to be less than going to be less than delta square times the expectation of x square divided by 3. That's an exercise. So if you set s to be at least 10 divided by delta square times the 2 norm, then you can bound the variance, and then the probability that x is not in 1 plus delta times its expectation is going to be at most 1/3. Now you could say we don't know what this 2 norm is, but by Cauchy-Schwarz we know that the 2 norm is always at least 1 over root n. So we know that by choosing s to be something like 10 divided by delta square, sorry, I should write this as 10 root n divided by delta square. By choosing s to be this, that will hold. And that ends the proof. So what you need is root n divided by delta square. Technically, you actually get something more nuanced. What you really need is 1 divided by the 2 norm. So the larger the 2 norm, the cheaper it is to approximate it. The larger the 2 norm, the cheaper it is to approximate it, and in the worst case, you're going to get root n. And so that ends the proof of the basic tester. So we need root n over delta square samples, and we have to set delta to be epsilon squared. And that gives root n over epsilon to the 4th, as is promised earlier. Any questions about that? Is that clear?
Could you go back to the other slide?
Sure. I'm guessing you want to go back even from here to here. Hmm.
Yeah. Why didn't we have like a XAB, XAB prime term?
I mean, I'm just using A to be the first and B to be the second. XBB prime doesn't make any sense. Right? I'm just
I mean that to indicate like
A was the first one, B was the second one. Which was the earlier sample?
okay, sure.
A is the earlier, B is the later.
But I mean I just mean in like counting like as two separate pairs of samples.
Yeah, exactly. These are two separate pairs of samples, right?
I know, but for example, like x1, 2, x2, 3.
Yes.
Like,
Oh, you mean that term? Did I miss a term over here? I think you're right. No, you're right. Sorry. That's my mistake. Um, so okay, so I should probably write this out as you have in this case these two are the same. In this one, these two are the same, and then you have a third one where I should say it's like something like x a b x b b prime, where a is not equal to b is not equal to b prime. You're right. My apologies. So I missed that term, and that adds a constant factor to the analysis, but that will also that will cancel. We can get rid of that just by upping the s by a constant. You're right. I missed that term.
okay.
But all of these terms are essentially identical, right? In terms of like you can bound them in exactly the same mechanism. Any questions? Yeah, could you crank up your volume a bit? It's a little hard to hear. Yeah. Yeah. Yes. Yes, this page. Correct. By this. Oh, so sorry. I maybe I went through this a little fast. So I wrote the variance as the expectation plus this term here, and here I can replace the 2 norm by the 3. I can replace the 3 norm by the 2 norm, and then I get this. Okay, so it's a slick. It's pretty neat that you sort of pull out this inequality at the right time. You throw it in, and you get exactly the answer that you want. You get the root n bound. It's yeah, sure. Oh, this is standard norm inequality. So for any vector, you get that the 3 norm is less than the 2 norm. You mean how do you prove this? Um, okay, so I'm essentially you can prove it using you can use convexity arguments. You can directly work out the math. Like this is the summation of xi cubed to the 1/3, and this is summation xi square to that. So you want to prove this inequality is true for all positive x, right? Because you'll take an absolute value over there, and you can basically prove it. You can, let me see, the quickest. You can probably use Holder. You can do you can directly manipulate the expressions to prove it, or you can use like convexity type arguments to prove it. So convexity is probably the easiest way to do it. It'll come out through an application of Jensen. Okay. All right. Any further questions? Okay. If not, then what I'm going to show you now is Paninsky's bound, and I'm not going to work it out in gory detail, so I'll let you sort of work out some of the lower order terms. So Paninsky in O of 8 gave an O of root n over epsilon square algorithm, or I should say a uniformity. His tester is, it is slightly different. It's essentially identical. So it's pretty much the same algorithm up to some lower order differences. One way that I like to view what Paninsky proves is he essentially shows that, essentially what he shows is that when the 2 norm squared is kind of like theta of 1 over n, then 1 over delta times the 2 norm samples give a 1 plus minus delta approximation. Right, so what we proved is to get a 1 plus delta approximation, we had a delta squared. Right, so we got this delta squared. And if you trace it back and you say, where did the square come from? The square came from Chebyshev. Right, it came from Chebyshev. Now, one way to look at this analysis is that it's kind of loose. The L3 norm and L2 norm, this is an inequality, and this is, of course, it is tight when X is concentrated on any one term. But there is some amount of slack here, and so that slack leads to a looseness in the analysis. And if you're more careful, you can actually get 1 over delta 2 norm samples, except Paninsky gives a direct way of arguing this, or rather what I'm going to give is a much more direct presentation of Paninsky's argument. Paninsky's paper is somewhat, it involves lots of calculations, but it turns out that with a few approximations, you can greatly simplify his calculations. So I will show that alternate presentation. I will say that this is not exactly how Paninsky describes it. This is my alternate presentation. And so what we're going to use is, given that we know Poissonization, you'll see that this is going to be a beautiful application of Poissonization. So an alternate O of root n over epsilon square. So this is a better constant algorithm using Poissonization. Okay, so let me actually just describe the algorithm completely. So I'm going to generate, and I'm going to call this K to be Poisson of M samples, where M I'm going to set to essentially be root n over epsilon square. Right, so I should say first generate K from this, then draw K independent samples, and his one difference is instead of measuring pairwise collisions, he measures the number of bins with more than one ball. Right? So in some sense, it's the number of items that are sampled strictly more than once. Right? That's the number of I guess elements seen strictly more than once. If this number, now he basically uses this number is more than, and so he explicitly writes out m squared over n plus epsilon squared divided by 2n. Reject, else you accept. So this is exactly what his analysis is. All right. So I think unfortunately I've fudged my sorry, I should say plus epsilon square m square, right? Okay. Yeah. So he says if the number of items that you've seen more than once is more than this bound. So again, this is m squared divided by n 1 plus epsilon over 2. Like if he sees it more than these many times, you reject, otherwise you accept. Okay?
What if it's like a distribution that like has like one really big weight, and so you see that bin a lot, but it only counts once?
So that's a good point. And so this is where I did a fudge. Okay, so the fudge that I'm going to do over here is I'm going to assume that for all pi, that for all, I should say for all I, pi times m is going to be much smaller one. So this is the approximation that I'm doing. And technically, Pandinsky fixes k. He doesn't draw it from a Poisson. He fixes k and he counts the number of bins with exactly one ball. You'll see that. So in the situation that you're talking about, it's actually very easy to reject that. You're right that this by itself might make an error, because you'll see this. Well, actually, no, sorry. Sorry, I take that back. So actually, this algorithm is going to work in that case as well. And so let me tell you why. So suppose you had this one bin that had extremely high probability. So there's only going to be one bin that has more than one ball. And okay, so sorry, let me answer this question. Let me do the analysis and then let me answer that question. Let me for now assume that pi times m is much smaller than 1. And that will take care of this case that you have. And then we'll come back and discuss how we can remove this assumption, because with this assumption the proof becomes extremely short. And you'll see exactly where things are going to start breaking down. Okay, so what is the expected number of bins with more than one ball. Okay, the expected number of bins. Now let xi be the number of balls in the ith bin. So by Poissonization, this is generated according to a Poisson with MPI. I think I've been using the notation there, MPI. And the xi's are independent. Xi's are independent. So now let yi be the indicator for the ith bin having more than one ball. In this case, so let's say what is the probability that yi is equal to 1, which is the expectation of yi. Now this is 1 minus the probability that xi is equal to 0 minus the probability that xi is equal to 1. And xi was drawn from a Poisson with parameter MPI. So this probability is exactly e to the minus MPI, and this probability is exactly e to the minus MPI times MPI. Here's where I'm going to use that approximation. If MPI is much smaller than 1, then e to the minus MPI can be approximated as 1 minus MPI. Okay, so I'm not working out the math in gory detail. I'm not doing it formally, but you can make it formal. It's not very hard. In which case, this becomes approximately 1 minus MPI minus 1 minus MPI times MPI. Okay, because I simply replace this exponential by 1 minus MPI, so I can put 1 minus MPI there. The probability that it's equal to 1 is e to the minus MPI times MPI. Just to recall that in a Poisson, your probabilities look like that, right? And we said maybe I shouldn't use k because I used k for something else like r. So r would be equal to 1 over here, and r is equal to 0 over there. Now, if you expand this out, the 1 cancels out with the 1. This MPI cancels out with that MPI. What you're left with is exactly m squared pi squared. And therefore, the expectation for the sum of yi is exactly equal to m squared times the 2 norms squared. So this is sort of an alternate presentation of the birthday analysis. I assume that MPI was much smaller than 1. I assume that MPI was much smaller than 1. I'll show you how to get rid of this assumption. I will have to change the tester a bit. Okay, so the expectation is this. The yi's are independent 0, 1 random variables. So now I can just use the Chernoff bound. So what is the probability that, let's say, y, which is the sum of yi, is going to be less than 1 minus delta times its expectation? This is going to be e to the minus delta square divided by 2 times the expectation of y. And now here's the key. If m is set to be some constant root n divided by delta, not delta square, then the expectation of y is going to be c squared divided by delta square. So I got the delta square n times the 2 norm squared. This I know is at least 1 over n, and therefore this is at least c squared divided by delta square. When I plug this back in over here, I'll get this is less than 1/3, because the delta square cancels out with the delta square. So I can get a 1 minus delta approximation for this expectation using root n over delta samples, not root n over delta square. Okay, so just putting it all together, I'm saying if for all I, m times pi is sufficiently small. Now, this, I'm not being very precise here, but essentially you can get this to work if, let's say, this was, if MPI was, I think, less than a half, then you can get all of this analysis to work out. Okay, you can get all of this analysis to work out if MPI was less than or equal to a half. Then, with c root n over delta samples, we can approximate, we can 1 plus delta approximate the 2 norm squared. Now, if there exists an I where MPI was greater than a half, now what does this mean? This means that there is a PI which is more than 1 over 2m, which is essentially, there is a PI which is more than delta square divided by 2c root n. So there is actually a probability that is more than 1 over root n. But this is easy to find. This is easy to find. Sample, or I should say draw, I'll say 10 times m samples with high probability the element I appears 3 times. And this immediately gives a method to reject, which is you could go back here and you could say draw 10 times, so whatever, m samples, if any element appears 3 times, then just reject. So with this step, we can take care of this fudge. This is not as elegant an algorithm because of this step. You can get rid of this step. You would have to do a more careful analysis. But it does show how you can get root n over epsilon square with a small trick, and using Poissonization, the analysis becomes really simple. I haven't seen this written anywhere, which I think is a bit of a pity, because if you look at Paninsky's analysis, it's actually fairly complicated. Although in effect he's doing essentially the same thing. He doesn't use Poissonization, so his variance calculation then ends up becoming somewhat involved. And there is, subsequently it has been shown by Diakonikolas and Kane gave an analysis where just the original birthday paradox algorithm can be analyzed with root n over epsilon square. But I like this because it's really something that is short and easy to show. So does this answer the question of how one deals with that situation?
Yeah, although it does, I guess, it does seem to me like it would make more sense to look at, like, if your probability distribution is far from uniform, it will have, like, if one of the PIs is large, then the other PIs can't also be very large.
Well, you have to
They
be
have to be much smaller than.
you have to be careful, like, because if one pi is actually 1 over root n, it's still in total variation can be very close to uniform because there's only one bin. There's only one element with high probability.
Okay.
So technically you don't even have to reject in that situation. You can still
Yeah,
accept,
that's true.
right? You only need to reject when there's this one element that has essentially like a constant probability.
Yeah.
So and the reason I put this step in there is simply so that the analysis will then go through without any problems. Otherwise, the problem, the issue over here is you need MPI to be sufficiently smaller than 1 to put that approximation in. But if you wanted to sort of crank out the expression exactly and go through it, you can still do it, and you would get, you'd start getting similar things, but it ends up being more complicated for that reason.
Sure.
So I hope that made sense. I was actually really surprised when I did this math and realized that it was actually that quick. And then the nice thing is with Poissonization, the yi's become independent, and then you just apply Chernoff, out of the box. You don't have to do any variance. You don't have to do any complicated calculations, and you also get a Chernoff type concentration, which in the other test is not known whether it concentrates that sharply. So here, the probability will go down very sharply, the probability of error. Okay, any further questions on that? So I can, let me take a, stop, pause for a few minutes. You can ask questions, and then I'll continue with the remaining topics. Okay, so now that we have uniformity testing, it is natural to ask about identity testing. So here, instead of uniform, you could say that Q be a known fixed distribution, and we get samples from P, and we want to accept if P is equal to Q, and reject if P minus Q in, let's say, L1 distance is more than epsilon. Right, so now here it doesn't seem like we can do the birthday paradox trick anymore, and that is because the 2 norm does not seem to have a clear relationship between this distance. We can only use it if Q was the uniform distribution. Except there is a really nice trick. There is a direct reduction to uniformity testing. So it turns out that I can actually plug in any uniformity tester. So what we're going to do is we're going to do a transformation which I like to think of as flattening. Transformation is going to convert Q into a uniform distribution over a larger support. And then over this transformed space, we can just do uniformity testing. Now, it's going to be convenient for me to assume things are discretized, and then I'll talk later a little bit on how you remove that assumption. So for convenience, let Q be discretized up to capital K. What I mean by that is that for all I, the probability can be represented as some little ki divided by k, where ki is a natural number, and of course k is also, capital K is some natural number. So what I'm thinking of is that all the probabilities can be represented as these integral fractions. So now it's sort of one way to think about this distribution. So let me write this as K1, K2, K3. So let me start from 0. And this is, of course, K4, so on and so forth. Right? So drawing from Q is equivalent to drawing uniform over K and then picking sort of the interval that you fall into. So drawing, and we've discussed this earlier in how to draw from a discrete distribution, is equivalent to choosing a uniform random element in K and outputting the interval the sample belongs to. Okay, so let me just do this more formally now. I'm going to use L of I to denote the partial sum, which is summation K of J going from 1 to I. Right? So LI's are the partial sums. And now let me describe the flattening of a distribution. This is a new distribution with support, that is K. So first draw I from this distribution, then draw uniformly at random from, let's say, Li minus 1 to Li. Should probably make that a plus 1. So I'm going to go in the opposite direction, which is I can think of to draw something from the support. I'm essentially going to choose a bin according to my distribution. So remember that X has support N. I'm going to construct a distribution with support K. So I pick a bin according to X, and then in that bin over here, I should call it a bucket because I don't want to, let me use the word bucket, not to confuse with the balls and bins. So let me think of these as buckets. So I'm going to pick a bucket proportional to using X, and then draw a uniform random element from that bucket. This gives me a distribution over K. Now what should be relatively easy for you to see is that, sorry, just a second. There. Is that the flattening of Q is uniform over its support. I leave the proof as an exercise. It's quite simple. So the flattening of Q is the uniform distribution. Essentially, we define the flattening so that this happens. Now the second claim is that if P is far from Q, then the flattening of P is also far from the flattening of Q. Okay, so the proof of this is we're simply going to just crank out the expressions. So let's see, what is the one norm of the flattening of P and Q? So I can write this as the sum of I going from 1 to n, the sum of j going from, I should say maybe I'll use j going from 1 to n, I going from L, how have I written this? Okay, so I going from Lj minus 1 plus 1 to Lj of the flattening of P of this element I. So now this is a distribution. I'm looking at the probability of that distribution on that I minus the flattening of Q, again of I. So I'm looking at this absolute value. Okay, so what is the flattening of P in some I, which is really just the probability that flattening of P, I should say, sorry. So this is the probability that P picks J, because you have to pick the correct bucket. Then within the bucket, it's uniform, and so you get this distribution here, and this is exactly P of J divided by Lj minus Lj minus 1. Okay, so plugging this expression into here, what we get is the summation of j going from 1 to n, and of I going from Lj minus 1 plus 1 to Lj. We're looking at the absolute value of P of j divided by Lj minus Lj minus 1 minus Q of j divided by Lj minus Lj minus 1. And this is simply going to give us P of j minus Q of j, because the denominator will cancel out with the summation, which is equal to P minus Q. So thus we get a square root k over epsilon squared query tester. Right, so we get square root k. Now you might say, but we get a dependence on k, not on the support, and we don't even know what k is going to be. Now intuitively, you could discretize up to n, and anything that's left over can kind of be ignored. One wants to do it a little carefully. One has to do it somewhat carefully, but by a This isn't very simple, but it's roughly the same idea.
Wait, I have a question. So
Yes.
like flat P is uniform and flat Q is uniform.
No, flat of P is not uniform. Flat of Q is uniform, and if P minus Q is more than epsilon in terms of total variation, then flat P minus flat Q, I guess in L1 or total variation, is more than epsilon.
Wait, isn't the flat of any distribution uniform?
No, no. So let's go back to what the flattening is. Flattening simply says that I'm going to pick a bin according to the chosen distribution and then spread that mass uniformly amongst all the elements here. So if my distribution, let's say that my distribution X only picked the first bucket. So let's say the distribution X is actually just only picking element 1. Then all the probability mass is here and there's no probability mass over there.
Okay. Wait, so why is flat Q uniform then?
Why is okay? So let's look at what is the probability that Q picks one of these bins. It's exactly K of I divided by
Size of
K,
the bin, yeah.
and that is K of I is the size of the bin or the bucket.
Yeah.
So it's basically flattening out that K of I uniformly onto everything here.
But why doesn't that also work for
I'm sorry, why doesn't that work for?
P?
So what happens? So P is getting flattened, but it's only getting flattened in certain intervals, in some of these buckets. So one way to think of this is, let's start with our original distribution. And let's say that it was putting some mass like this, where this is going from, 1 to n. What this does is basically it sort of flattens out some of the, but in parts where it's empty, it's still going to be empty here.
But won't that bin not have like the KI will be zero, so it won't.
No, no, no. The K's are defined with respect to Q, the fixed known distribution.
Oh,
These are all defined with respect to Q. Maybe this was not clear. I should have made this. This is specific to the known distribution you have. So you have this hypothesis distribution, you build the flattening which is perfect for your distribution, and then you flatten the unknown distribution according to it.
according to that, okay, that makes a lot more sense. Thank you.
So obviously you need to know what these KJs are to be able to do the flattening, which means you need to know the distribution explicitly. But that's the assumption, right? So you know the distribution. And this is essentially the same as, remember we discussed this a number of lectures ago where we had the opposite problem. We could sample from the uniform distribution and wanted to be able to sample from an arbitrary discrete distribution, and this is the trick that we did. And now we just sort of invert that idea. So we say that actually gives us a mapping that goes from the specific discrete distribution to the uniform distribution, and we use that same mapping, which depends on Q. We use that same mapping for the unknown distribution. And how do we do that? We do it explicitly in this way, right? We draw I from this unknown distribution X or P, and then we just draw uniformly in Li minus 1 plus 1 to Li. And this gives us a distribution with support K.
Okay, that makes sense. Thank you.
So by non-trivial reduction, one can show like K can be set to something like 6 times n. This needs to be done a little carefully because the true distribution might not be discretized up to n, but what you do is you take away the remainders and then you sort of randomly put them somewhere else. So I'm not going to get into that specifically. So as long as you understand this idea, I should say that it's not hard to see to set k to be something like, I should say, sorry, n divided by epsilon, right? Because you could say that every qi can be rounded to the nearest multiple of n over epsilon and only affect the L1 distance by epsilon. But to round it down to exactly something times n independent of epsilon requires a little bit more care. So the final point that I want to make is the lower bounds. And so the theorem, so there was one by Batu et al. Showed that any uniformity tester requires omega of square root n samples, and then Paninsky, he showed a tighter lower bound of root n over epsilon square. So Paninsky gave like this optimal analysis, but it was known from earlier on that root n samples suffice, and again this was again implicit in Goldreich and Rahn in '99, who also have made similar arguments to this. So what is the proof idea? The details tend to be a little painful to write down explicitly, although they're not hard once you have the main idea. So think if there's an adversary holds two distributions, or it's actually two distributions of distributions, one of which is called yes, one of which is called no. So the yes is just the uniform distribution, and the no is going to be, one can think of it as, let's say, a set of distributions far from uniform. The adversary holds two distributions. So now here's the algorithm, which is the uniformity tester. The adversary is going to pick from one of these and give samples from one of these distributions to the uniformity tester. And the uniformity tester actually just needs to distinguish and say, did it come from this distribution or did it come from the no distribution? So what we'll say is that now let's actually scrap the uniformity tester. Consider any algorithm. The algorithm needs to determine which, like from the yes or the no, which distribution the adversary chose. And clearly a uniformity tester would work for this problem. Because a uniformity tester can distinguish between these. But we're just going to have a setup where the algorithm simply needs to determine which it comes from, a uniform or this specific set. It's not the all distribution, some specific set. But the algorithm could do much more than using a uniformity tester. It could do whatever it wanted. Now we choose the no set or distribution such that little o of root n samples cannot distinguish. And so thus a uniformity tester requires, omega of root n samples. So we need to choose this no distribution in such a way that square root n samples cannot distinguish between these. And this is also often referred to as statistical indistinguishability. Indistinguishability. So what this means, statistical indistinguishability means that a set of little o of root n samples has the same distribution over yes or the no. Okay, so now let me be a little bit more precise. So remember, the yes distribution was simply uniform. The no is going to work somewhat more carefully. The adversary chooses a uniform at random subset of n over 2 elements in n. So let me refer to this subset as S. Then the adversary provides the uniform distribution over S. So it's important that the adversary first chooses a support randomly, then provides a uniform distribution over S. So this is like the yes box, which is just a uniform distribution, and this is the no box. Remember, this happens in the beginning. After that, when the algorithm queries from it, it's only getting uniform samples over S. So this first step doesn't happen every time there's a sample. This happens at the beginning. So the adversary is either going to show you the yes distribution or is going to pick a uniform random subset and provide a uniform distribution over that subset. The algorithm needs to distinguish which one it is. Now note that these are all have L1 distance omega 1 from uniform. Now, I'm not going to work the math out explicitly, but you could see that by the birthday paradox calculations, a set of little o of root n samples with high probability gives all singleton bins. Right? So if you chose less than root n samples, in either case, all the samples are just going to be distinct. That is, all distinct samples. Therefore, roughly speaking, for any set, which I'll refer to as, because I used S already, T of samples, the probability of seeing T from the yes or the no is roughly the same. And so essentially it's about looking at the birthday paradox and observing that if you did less than root n samples, then all the bins are essentially singleton bins. Or rather, all the samples are distinct because the no distribution is essentially just a uniform distribution over a smaller set, but it's a set of size n over 2. So in anything, in lit low of root n samples, all the samples will be distinct. And when all the samples are distinct, there's really no way of distinguishing the yes from the no. The full calculation analysis has to be done somewhat carefully, but this is the basic argument. So I'll stop here and I'll take any questions. And this is going to end our discussion for uniformity testing, and the next lecture will start something else.